again, if you have not started studying for the midterm, please do so. It will be through chapter 12. We will not cover protecting groups in that, but I will assign homework in just a little while. Let's take a look at chemoselectivity for sodium borohydride and lithium aluminum hydride. This is something that I wanted to talk about last lecture, and we didn't really have time to go through that. Also want to talk to you about some SN2 reactions that are important. And then we'll look at some homework. All right, talk this out with someone next to you and see what you think might happen.
One of these into as to which one it is.
My guess would be the top one on the because
It was the more stable.
I was gonna say it's not
Or no,
shielded
it
by
wasn't.
a very near like
The other one.
a
So in
little
page
thing.
4.
I think LA is just gonna take over and stuff.
Well, yeah, the LA
Oh, yeah.
AH one.
I think LA is just
LA, yeah, because you said that one was like more.
more reactive.
Yeah.
So let's do that one. Actually, don't even write it out. But
I don't think we're wrong about that one. I don't know about the other one.
she said maybe the bush will write the right one.
I think it should be both.
I think it would be friggin'
Oh, SABH. Or convert it.
we'll convert the cyclic alcohol, not the phenyl chain alcohol.
Yeah.
Because you've got that janky nitrogen and that janky oxygen. So
Well,
you think that oxygen's gonna get broken in?
Yeah, that's done.
I think it could be that one too because
Same thing here.
there's more resonance with the nitrile group and the oxygen, the other oxygen.
Oh, it's
So it'd be more stable, I think.
Give me your picture. Give me your
yeah, I think you're right.
Wait, hang on, don't use that one, actually. Use one that I never used.
Do what?
Don't mind my green fuzzy socks for Christmas. It's 19 degrees outside.
So we're gonna be
I think so.
Caleb, I don't think that O here will be.
No,
Oh, I
he's
meant
talking
it.
about this one. He thinks this one will.
For
Oh,
I think that might happen with lithium aluminum hydride, but I don't think it would. That's
But then
possible.
we'll have to take out the.
Or you could form a double bond. No, you couldn't. You're right. Yeah, that's not you're right.
that's really interesting.
Then have this up on here. So what about these over here?
So we think that this one will only probably that one.
And this one will come here.
Well, no, I think this one will do both of them, because this is not as reactive as lithium hydride. And I think it's often in that knife dot or shielding, this one like he was talking about.
With this one, I'm not really sure on this one because
This one is, the LAH is just strong. Does that have anything to do with surgery?
I don't answer.
no, I don't think Sarah can answer.
Yeah, I don't think that has anything to do.
But I don't know if this
But
one would
still,
be.
it's kind of open still. Doesn't look that bad.
Break that bond.
Yeah, but the one is one of the new things like more resonant stabilized like the inside.
Oh,
But
It's not as good as
it's not
the
anything, yeah, so.
Well, but even then, if you take bigger material electrons, that's probably gonna be more stable than the one out here.
Yeah, this is an option that it can't go to. Because sodium borohydride carbonate is not deprotonate, so what would be? Alright, in the meantime, I'm gonna play my phone.
That happened the last time we had
He's
last
drawing it.
Monday.
I think it would also be
It happened Wednesday.
Yeah, it's really, looks really bulky, right?
I'm also gonna introduce one that's not in your book, for this chapter as well. It's called Dibol, diisobutyl aluminum hydride. It actually exists as a dimer. Shares, the hydride with another one. You don't need to know that. But it also has some chemoselectivity that I'd like to talk about as well. So it has two isobutyl groups attached to the aluminum. This is an electrophilic reducing agent, whereas these are nucleophilic reducing agents. Okay, what do you think about LAH? Let's go there first.
It's only gonna do something to the ester, it's gonna take off the carbonyl and then turn the COH, or the COCH3 into COH.
Okay,
And
so you think it's gonna affect the ketone,
I think it's gonna affect the ester.
ester, okay?
I think it'll be both.
Something will do both. What about the nitrile?
Gonna leave it alone.
You think it might leave it alone? Okay? Anyone else?
well, the sodium borohydride, it doesn't work on esters.
Okay,
The LAH does.
good,
But
good.
the LAH would also take the methyl off, I'd say, because it does reduction.
Okay, so sodium borohydride will actually not touch the ester. Okay, so that's good. Okay, it will touch the ketone. It will not touch the nitrile. Okay,
It won't change the ketone in the ester.
it will not, this is not a ketone, this is an ester.
Yeah.
Yep, that's a ketone.
I meant carbonyl.
Yeah, yep. So sodium borohydride will not touch esters. So that's probably the most important chemoselectivity to talk about in this chapter, okay? Sorry.
What kind of reducing agent is the dibol?
An electrophilic reducing agent, okay? Formed a chiral center there. We still had a chiral center here and here, so this is still So, lithium aluminum hydride, it is stronger. What do you think is going to happen?
Protonate growth
It will
carbonyl.
affect the ester.
By taking, the oxygen on it and making, it would be an OH group, of the OCH3, turns it to an OH.
Okay, so primary alcohol, secondary alcohol,
Well, that would be a primary alcohol.
primary alcohol. Okay, what else is it going to do? Or is it going to do anything else?
Reduce the ketone.
Reduce the ketone. And what else did it do?
It did something.
It reduced the nitrile. Okay, so this is a nitrile group. Reduce the nitrile group to an amine. Amine group.
Oh, you forgot a oxygen. I think.
Did I forget an oxygen?
Yeah.
So what happened to the carbonyl group?
Oh, the
It
oxygen
isn't that
methyl.
kill the alcohol also? Or there still should at least be an oxygen.
Nope.
It cancels.
Nope, we're good.
Cool.
What happened to
Good.
it though?
Let's look.
It's that high.
Let's look. Carbon, 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 carbon.
So does it just kick the oxygen off entirely?
Oh yeah, oh yeah.
Becomes
Absolutely.
H2O?
No,
Oxygen is actually.
if this is completely gone, right, then this is going to get quenched
Oh.
as,
Okay, I thought the carbonyl one was what you said got kicked off. Okay.
it's going to get quenched as ethanol, right, at the end. It'll be gone.
Why did the nitrile group move to be
The nitrile group didn't move
or not move, but switch? Like,
because, take a look, it's got 3 bonds. Can those get reduced to a double bond or a single bond?
Yes.
Yes, they can. So this is still reduction. So consider a hydride attacking here, kicking electrons up to here to get a hydrogen here, another one coming in, kicking electrons up to here, getting another hydrogen here. Yep, so reduction in this case is getting electrons from the H minus, and therefore you should have gotten, like that, 2 nucleophilic H minuses that attack that carbon right there. Yep. Why is it electrophilic? Nitrogen is more electronegative than carbon. So there is a slight dipole that exists between these two.
So if there's any double or triple bonds, LAH will always reduce, it reduces all double and triple bonds?
It does not. It will not touch, alkenes. It will not touch alkenes.
Or alkynes?
Or alkynes. That's right. It will not touch alkenes or alkynes.
But it'll touch everything else?
For the most part. Yep.
Anything with a dipole? Or any double bond or triple bond with a dipole?
I would say anything with unsaturation that has the ability to accept electrons as an electrophile. Yep. All right. This one's a little interesting. This one does something a little bit different. What do you think that it might do?
Only to the nitrogen and nothing else.
Only do the nitrogen and nothing else. Nope. Just look at the reagent. Why? What do you get from looking at the reagent? That's why I drew it out.
It's bulky.
It's bulky. So do you think it's more reactive or less reactive than LAH?
Less.
It's less reactive than LAH. So that is true. It's less reactive than LAH. However, it will still reduce the ketone to the hydroxy group, okay? And you might actually get a mixture of some of this. The more common one that you see is actually using one equivalent. Now again, I don't know if it'll work under these circumstances, but using one equivalent in the presence of an ester will allow you to stop at the aldehyde. And that's a kind of really good reaction, because if you want to take this to the aldehyde and stop it there without doing another reduction, it's a great synthetic tool to do so, okay, without going all the way to the primary alcohol, okay? It will also reduce nitriles to alcohols as well, which is very interesting.
Do you mean aldehyde?
Yeah, to aldehydes, sorry. Yep. Yeah, it'll reduce nitriles to aldehydes. Now this only happens because you have to have a source of oxygen. This only happens after the quench, okay? So Dibol's got a quench, and let's see if I can find it. Again, it's probably gonna have water. Yep, that's exactly what it is, water.
So it reduces esters to aldehydes too?
Yep. Again, as long as you use one equivalent. Now here, clearly you would have to use 1, 2, 3 equivalents of this. So what I'm saying is in this particular case, it might not give you just this selectively. In other cases where you only have one group that you're trying to reduce, then using one equivalent would be ideal.
This is a question I probably should have asked like forever ago. But when you're writing water in an equation versus hydronium, does it matter which one you write?
Yeah, it does, because if you had a group in here that was acid sensitive, you would only want to have water around.
But isn't hydronium always present when you have water?
In extremely small amounts, right? Right? I mean, you gotta think about the what's that? The KW, right? So the KW tells you that hydronium is present in a very, very, very small concentration anytime you have water. Okay. Yep. Good question. Other questions? Okay, let's take a look at, the book actually has SN1 and SN2.
Okay, we never talked about IV pack.
I'll get there.
Okay.
We'll end with it. Go ahead and try and react that one. Go ahead and try and react that one. Ask yourself, do chemists still use simple reactions like SN1 and SN2, and I will tell you all the time, especially SN2 chemistry. It's the most common. I was in an interview one time, and they were asking me a synthesis question. They said, how do you think this reaction proceeds, or what would you do to make this transformation, a synthetic transformation? And it was very simple. The answer was just an SN1 reaction. But when you've had so much education, you think about all those other reactions that are out there, and you're like, it's got to be something more fancy than this and everything. And that's all it was. It was an SN1 reaction. So sometimes the simplest answer is the best one. Okay? No? All right, what do you think's gonna happen first? Alex?
So what I did, I don't know if it's right, but I made the OH get the H,
Yep.
the water,
Yep.
and the BR attack.
Yep, that's good. Okay. So first thing is the OH is going to get the proton, right? You make the oxonium ion. Oxonium ion. And the oxonium ion wants to do what?
Get out of the operate.
Leave.
Leave to become
Water.
water, okay? So it leaves to become water. What does that leave you with?
Charged carbon.
What does that leave you with?
Positively charged carbon.
Yeah, carbocation. That's the word people were looking for. And it'd be a tertiary carbocation. And it's gonna leave first before the attack. Why? Why wouldn't it proceed via SN2? Why wouldn't it proceed via SN2?
Because the attack can't occur until there's a positive charge on the carbon.
Nope. There's a different reason why it can't attack.
Well, wouldn't it, if it, the bromine attacked first, wouldn't it just take the hydrogen of OH instead?
Oh, no, I'm talking about if this is here and it wants to attack to kick the water off, what's in its way?
The water?
The methyl group. The methyl group. Sure, the water too, because it's all bulky, right? It's all bulky, but that's the reason. There's it's too bulky, and not only that, that carbon's happy, really. It doesn't need anything. It's happy until the water leaves, right? Okay.
What would the bromine be attacking if the water was still there? Like if
Exactly.
no, like this.
The bromine has nothing to attack essentially because it can't get there. Not only that, but the electronics on the carbon are they're just not there yet. Okay, until it starts to leave. Now, Riley asked me this question last semester, and that is, why in SN1 chemistry do you get a little bit more of the inverted product as opposed to the 50-50 racemic mixture? Why is it somewhat inverted? Why do you get some of the inverted product or more of the inverted product?
What do you mean inverted product?
Yeah, so if this was a chiral center, okay, which it's not, okay, if it was, why does the bromine preferentially want to attack more from the back side than the front side? If water is in the front, if water happened to be in the front,
Are you talking SN2?
why would it be more SN2-like in the product of the answer?
Is it because the water is in the way as it's leaving, so the bromine can't come around?
That's
and
right.
attack from that side?
The water's in the way while it's leaving, and so as it's leaving, if there's a bromine coming in, it will preferentially go to the opposite side. So you actually do get slightly more inverted product as a result of that leaving group coming out that's bulky, and there's more room on the backside. Yep, that's really good. Okay. Caleb, you're gonna survive. Just giving you a hard time. Let's look at this reaction. This one's really interesting. SOCl2 looks like this. All right, without looking in your book, pair up with somebody and try and come up with the mechanism. I go from here to here. This is thionyl chloride. Thionyl chloride. We need it in the presence of the base too. The base that they're using is pyridine.
What do the equal signs mean?
Oh, I just put equal.
Okay.
I didn't mean to.
Yeah.
Sulfur would be resonance stabilized. Because sulfur wants to have 3 bonds, it has 4.
So does like the chlorine attack the hydrogen?
Isn't sulfur one of the weird ones that can have an expanded octet?
Yeah.
Like it irregularly will have
Yeah,
like.
but that would make sense though, if you have a chlorine come in and take the benzene. Well, no,
So
because then we only have 2.
what you said, sorry, what were you saying?
The one that
This class should not be at 8 a.m. I said this class should not be at 8 a.m. My brain is not on yet.
Let's see what it looks like being attacked. We need this hydrogen. No, we need the OH off. So how do we get it off?
It's not, so you make it.
The only thing that can get it off is by attaching it to the soap.
Or wait. What does CO find the hydrogen, make hydrochloric acid?
Well, okay, so that's what I thought, but then that wouldn't make sense because then you would still have to have, unless the HCl would dissociate. Actually, yeah, that could be it because the pyrimidine could take the hydrogen.
That's what I'm saying.
I think, hang on, let me draw this out.
Well, if we take the H out, we will have the oxygen, and how are we gonna get rid of the
No, because you still have an oxygen that has
Oh,
it.
wait, hang on.
So we can use the
H off that.
maybe. We will you get this sulfur to like attach to the oxygen, and then discard one of the chlorine, and then the chlorine, later in the
Are you saying
attachment.
that this will take oxygen if they actually
I mean, it would attach here, and then.
But it's only gonna take the proton, it's not gonna take the
No,
oxygen.
to the
After
oxygen,
the-
it will attach to the
Yeah,
oxygen.
after the hydrogen leaves your HCl.
No, like with the hinge there, and then they say when you will attach to the oxygen, and then discard one of its CL, and then other intermediate there, and then one of the chlorine will come. The chlorine that is, and then
This will give you a little bit of a hint to the reaction mechanism.
So, O is SO. So what's because the alcohol is not a good leaving.
how many steps?
There's another reaction that will do this too. You do not have to know the mechanism of this next reaction. Hydrochloric acid in the presence of zinc chloride. But that will also do that same reaction.
No, maybe that converts.
What is 2NCl2?
That's zinc chloride. That's a Z.
Oh.
That's a Z.
I'm not gonna lie, I'm kinda stumped on this one. I have ideas, but I don't know how it's gonna work.
Okay, great. You have ideas.
Yeah.
That's, go ahead.
It goes something like hydrochloric acid, but that might just be horribly wrong.
Okay,
Well-
so it does produce hydrochloric acid in the end. Yeah, it does.
But you need, right now, you need something to get the alcohol to leave.
You do need something.
That's what's stumping.
You do need something to get the alcohol to leave, but
Because
look,
alcohols are not
but
gonna
look
leave.
at the mechanism, or not the mechanism, but look at the next reaction down and it will tell you what gets the alcohol to leave.
Giving the base.
The chlorine gets the alcohol to leave. Why? How do you know that?
Because it's an SN2 reaction.
Because it must be SN2 and it must attack from the back side because the chlorine's there and it is on the back side. So the chlorine is what gets the alcohol to leave, but there has to be something else attached first.
That's what I can't figure out.
Uh-huh. No.
It's not just the entire drive, that's the final chloride, is it?
Would it just be a hydrogen to make the oxonium again?
So do you get an oxonium first?
There's no hydrogens to go
There's,
around.
yeah.
Ah, you don't need a hydrogen, but she is correct. You do get an oxonium first.
So
Okay?
where does it come from?
Ah, it comes from the fact that this is a nucleophile and this is an electrophile. So the first reaction is the oxygen attacking the sulfur, okay? Kicks the electrons up. What's it gonna do?
Beat.
Go ahead and draw that. Go ahead and draw that. The oxygen with the hydrogen still attached is going to attack the thionyl chloride first. Let's just do it. Okay, you haven't learned this particular intermediate quite yet. This is a tetrahedral intermediate. Anytime you attack a ketone or a thionyl like this, or an aldehyde, as an electrophile, a nucleophile to an electrophile, you get a tetrahedral intermediate that stops there, okay? The next thing is the collapse of the tetrahedral intermediate. And you're gonna kick off the chlorine. Still have the oxonium. And one chlorine here. Now what's gonna happen?
Chlorine will,
Nope. You got something else in here. The pyridine's gonna soak up the proton now, okay? Pyridine's got the proton now. Very interesting thing happens in this last step. How do you think sulfur likes to leave as a leaving group in this instant? With the oxygen still attached, okay? How about the oxidation state of sulfur? The oxidation state of sulfur. Would it rather be a +4 or a +5? We already know it has no problem being a +6.
So yeah, +4, maybe +4.
Yeah, it's +4 is what it would rather be. So watch. When the chlorine comes back around for the SN2 reaction here in the end, it actually does a fragmentation to produce sulfur dioxide. See it? This is what forms the sulfur dioxide here, the SO2. The chlorine comes off, and then in the end, pyridine still is soaking everything up to make pyridinium chloride, or pyridine times HCl. And there it is.
I don't know how to do with that reaction.
Okay. We didn't have time to go over IUPAC nomenclature of cyclic alcohols and phenols. Please do so on your own. We can review that on Monday. Quiz, I will again post a quiz today. You will have that available to you over the weekend. And I hope you guys have a good one.